Okay, so now we are ready to define ordinals. Before that, let's prove this theorem that we promised from last time, which is that if you have two well orderings, A and B, with orderings less than A and less than B respectively, and they have the associated epsilon images alpha and beta, then these two well orderings are isomorphic if and only if their epsilon images are equal. By equal I mean exactly equal as exactly the same object, the same thing, the same, not just similar, exactly the same thing. Let's do this proof. Let's start with the easier direction, which is going this way. Well, in this case, we had from the observation at the end of our last class that every well ordering is isomorphic to its epsilon image, right, with the belongs relation. So now we have that A less than is isomorphic to its epsilon image alpha with the belongs relation as the relation, which is, we're assuming, is equal to beta, which is isomorphic to B less than B. So we get that A is less isomorphic. So that's very easy. The other one is the direction that is a bit more interesting, and it's also not hard, but it's a good application of transfinite induction. So let's go through it. Okay, so we are going this direction. So we assume that these two guys are isomorphic, so we consider an isomorphism. So let F from A to B be an isomorphism. What does isomorphism mean? Maybe we just put it on the side. It means that F is bijective, and it means that if A less than A prime according to A, that's equivalent if and only if their images are related the same way. F of A and F of A prime are related the same way, but now these images are in B, so this is according to less than in B, while this one is less than in A. Okay, so when you go through F, the relation between the elements gets preserved exactly the same way. So the orderings are mapped the same way through F. So it's an isomorphism, meaning it preserves the relation. So they both look exactly, the orderings look exactly the same according to F. So now what we want to do, we're going to use transfinite induction to show that the epsilon image of an element A according to A is equal to the epsilon image of F of A, now according to the linear ordering B. For all A, for all little a in A, for every little a, this image is the same. So how do we do this? Well, let's use the standard induction. So let P be the set of all the little a's in A. Remember, when we want to do something in induction, if you're going to do it clearly, let's always do it this way. P is the set of all the guys that satisfy the property that we want. Meaning, when we do the epsilon image of little a, according to the linear ordering A, let's put, is equal to the epsilon image of F of A. This little a and little b that I'm putting down here is because the definition of the epsilon image depends on the well ordering A. So essentially, this function, you will have like two different functions E, one for A and one for B, according to this definition. So that's what that means. This is according to little a, this is according to B. Now, if we're going to apply transfinite induction, let's see what induction says. It says that if you have a subset B, which now we're calling this guy P. Right now, this guy is P. This one here is our P right now. And we want to conclude that P is equal to A. That's exactly what we want. And for that, we need to show is that for every T, if the segment below T is a subset of the whole P, then T belongs to P, right? Okay, so that's what we need to show. So let's do that. Consider an element T that belongs to A. Suppose that the segment of all the elements below T is included in our set P, we want to show that T belongs to P. Correct? That's what we need to show induction. Well, let's see how that goes. So that means we want to show that this thing up here holds for T. So let's see what we get. E, according to A of T, is equal by definition to E of S for all S that is below T, that belong to the segment according to A of T. Correct? That's what the definition was, right? Of E, exactly. E, all the previous ones. And this is, of course, E according to A. Now, by the induction hypothesis, we are assuming that the segment of T is included in P, right? So all these S's belong to P, right? And if they belong to P, that means that E of them is equal to the same thing on the B side. So by the induction hypothesis, this is induction hypothesis, we get that this is equal to E according to B of F of S, where for S in the segment A of T. Good. But now F is a bijection. So F of those guys is exactly, let's call them something else. Let's say that we use R for F of S. So this is exactly F E of R for R below F of T, right? Belonging to the segment of F of T, right? And this is because it's a bijection, right? F of S is below F of T if and only if R is below, S is below T if and only if R is below F of T. And that's the same thing as E of F of T, right? So that's how we conclude that T belongs to P. That's the property that we wanted, right? That E of T equals E of F of T. That's how we conclude that T belongs to P. And that's what we wanted for our induction hypothesis. So we proved that P is everything. And therefore, these E's are all the same. And therefore, we get that alpha, which is the range of EA, is equal to the range of EB, which is equal to beta. Right, because EA is essentially the same as EB. They give you the same image. The ranges are the same because that's what we had just proved. Sorry, I meant here beta. Okay, so we got that two well-ordered are isomorphic if and only if their images, the epsilon images, are equal as objects. So that's exactly what we want, right? That's what we wanted when we said we want a representative. So now we have, for the whole equivalence isomorphism class of a well-ordering, like we can group all the ones that are isomorphic and use its alpha as the representative for all of them, the epsilon image. So then we're going to say that alpha is an ordinal number if it's the epsilon image of somebody. So everything that is the epsilon image of somebody is going to be called an ordinal number. And they are just representatives for well-orderings in this sense. Cool. So, theorem. We can characterize ordinals this way. So, alpha is an ordinal if and only if it is transitive and the belongs relation is a well-ordering on alpha. Right? So, it well-orders alpha. This direction is quite direct, right? Because if alpha is epsilon, the epsilon image of A, then we know from our last week video that alpha must be transitive, right? And we also know that alpha is isomorphic to A, and A is a well-ordering, so it's isomorphic. I mean, the orderings look exactly the same. It's a complete bijection between them, same properties. So if A is a well-ordering, then alpha must be a well-ordering too, right? So then that direction we get pretty easily. The other direction it's a bit more interesting, but it's quite easy. And to see that is that alpha is the epsilon image of alpha. If we know that alpha is transitive and it's a well ordering. How do you show that? We use induction on epsilon alpha to show, which is a well ordering. We're assuming it's a well ordering, to show that for all beta that belongs to alpha, the epsilon image of beta, according to this alpha, is equal to beta. Okay? And again, how do you do that? Well, it's just the usual proof. Let P be the set of all betas that belongs to alpha such that according to the epsilon function, beta gets mapped to beta. And now we have to show, consider a beta such that with the segment of beta including P, we want to show that beta belongs to P, right? That's what we need for the induction. So that we need to show that beta satisfies these things. So what happens? What is this? Well, let's see what E alpha of beta is. Well, this is by definition the set of all E sub S for S that belongs to alpha and S epsilon alpha beta, right? So essentially all the S's that are below beta according to alpha. And here's where the transitivity comes in. Transitivity comes in because these two properties up here are equivalent to saying that S belongs to beta. If S belongs to, if epsilon alpha means belongs, right? So obviously epsilon alpha implies that it belongs to beta, right? Because epsilon alpha was essentially belongs but restricted to alpha. The other way around, if S belongs to beta and beta belongs to alpha, by the transitivity of alpha, that's where we're using the transitivity of alpha, we get that S also belongs to, S epsilon belongs to beta. So that's how we just get here that this is the same thing as ES for S in beta. But then by induction hypothesis, we know all these S's are below beta, right? So then this is exactly the same as S for S in beta. And S for S in beta is just another word for beta, right? So that's how we get that beta belongs to P. That proves the induction hypothesis, the assumption for transfinite induction, and therefore we get that P equals A. And now that implies that the range of that E applied to all the elements of alpha is actually equal to alpha, because it's all the betas for betas inside it, and therefore alpha is an epsilon image. In this case, this implies that under these assumptions that alpha is transitive and well ordered, alpha is the epsilon image of itself, and therefore it's an ordinal number. Okay, so that means we this definition here, you're an ordinal number if you're the epsilon image of somebody, is a bit indirect. This one is very direct. You have a concrete property of what it means to be an ordinal. You have to be transitive in the sense of this property up here, and you have to be, and the epsilon relation, and the ordering has to be a well ordering on you. We're gonna see later that actually you don't need well ordering. All you need is clean ordering if you have the foundation axiom, which we don't have yet. But okay, that's fine. We have a class. Cool. So that's our ordinal numbers, transitive sets where the belong relation is a well ordering, and they satisfy the property that if any two well ordered are isomorphic and if and only if their epsilon images are these guys, and they satisfy the property that the epsilon image of themselves is themselves. Just one more thing to comment. Could you be transitive and not well ordered? Let's see that in class. See you guys later.